Hello, this is Magnus Halldórsson speaking from Reykjavik, and this is joint work with Marek Sigan and Guy Korsars. So we are dealing with this classic set cover problem. It's one of the top 10 NP complete problems. We're given a universe of n elements and a collection of subsets, and we want to find the subcollection that covers the whole universe, minimizing the size of the subcollection, namely the number of sets in it. And this is well understood. The greedy algorithm is log and approximate, and that holds actually for various extensions, but it's also known to be essentially best possible you can do in polynomial time. So what is there left to do? Well, you could ask, what if we are allowed more than polynomial time, but still less than exponential, because fully exponential, because then you could just solve it optimally. Now, when we deal with exponential time or sub-exponential time algorithms, then using NP hardness and P versus NP as an assumption doesn't help very much. So we typically use the following one. We assume that there are no 2 to the little of n time algorithms for 3 satisfiability, where n is the size of the Boolean formula. So this is called ETH, or exponential time hypothesis, which is standard when dealing with sub-exponential time algorithms. Now, there's a positive result for set cover with an algorithm that is exponential in n to the alpha, where alpha is some constant between 0 and 1. And then you can reduce the approximation factor by 1 minus alpha. And this is by Sigan et al. From 2009. Now, in terms of lower bounds, we don't quite have matching lower bounds, but the known standard lower bounds can be translated here to give a lower bound that is matching up to a constant factor, except that the constant is now in the double exponential, the double exponent. So that means that this actually only tells you something when alpha is fairly small. And so the interesting question is, well, what if, say, alpha is half? What can you actually achieve? And we resolve that essentially by showing that the upper bound is essentially tight. Namely, there is no algorithm achieving 1 minus alpha times log n approximation that runs in less than exponential of n to the alpha minus delta, where delta is arbitrarily small constant. And this, again, is assuming ETH and nothing else. Now, we also have a second contribution in this paper. This is for a generalization of set cover. There are 3 problems that we essentially tackle, or give an algorithm that works for all 3: directed Steiner tree, connected polymatroid, and submodular cover. And for that, we give an algorithm that is kind of a similar complexity as for set cover, but only holds when alpha is greater than half. Now, let's focus on the lower bound result. And the hardness results for set cover all go through this problem here that is closely related to PCP theory. This is called the label cover problem. Now, rather than actually going through this whole fairly complex definition, let me point out that there are essentially 3 notations here. There is the size of the formula, size of the graph, sorry, which I denote NLC. There is the number of letters in the alphabet size. And the third term is the epsilon, is the how good of a inapproximability do you actually get. So this instance contains involves a certain bipartite graph that is labeled, has some constraints. And the key thing is that the PCP theorems are essentially reductions from satisfiability to label cover, such that if you have a satisfiable SAT formula, then all the edges of this label cover instance are satisfied, namely these constraints that are given on the edges are all satisfied. If, however, you have an unsatisfiable SAT instance, then you get a large separation, namely you can only satisfy a very small fraction of the edges, only an epsilon fraction. Of course, the smaller the epsilon, the better the separability. And you can view the set cover hardness result as basically two steps reduction. You reduce 3 SAT to label cover, and this is a PCP theorem. And then you reduce label cover to set cover. And this is we base this on a reduction by Moskowitz, who actually modifies a reduction by Feige. And Moskowitz uses the PCP theorem of Steiner and Storer from 2014. Now, if we look at these parameters that are involved in that PCP theorem, so we call that N is the size of the three satisfiability formula. Then the size of the label cover is polynomial in N. The alphabet size is polynomial in 1 over epsilon. Now it turns out there's another older label cover construction or PCP theorem that is relevant here. It has a better size guarantee. It's a nearly linear size. But the alphabet size now is exponential in this sensitivity parameter, epsilon. And what does this really mean? Well, for us, this is crucial because in the reduction to set cover, this sensitivity, 1 over epsilon, basically polynomial, polylogarithmic. And the size of the set cover instance, you have the number of elements, which is some polynomial in this label cover size. So the polynomial gets bigger and bigger as alpha gets bigger, gets smaller. And the number of sets in it is linear in the label cover size and in the alphabet size. Now, because of this, Moskowitz used this label cover construction of Steiner Storer because it ensured that the alphabet size wouldn't be a problem and cause a super polynomial number of sets. This is why you couldn't use the reduction of Moskowitz-Ras because the alphabet size would make the set cover instance size actually blow up. On the other hand, for our purposes, we are dealing with sub-exponential-time algorithms. And that means that this size blow up is a serious issue for us. It means that the lower bound factor becomes then factor 3 worse, essentially, in the double exponent, whereas the blow up in the number of sets is not a problem. So you could say that we make a very simple observation regarding the use of this in sub-exponential-time algorithms. You need the Steiner Storer for NP hardness, but it's more efficient to use Moskowitz-Ras for sub-exponential-time hardness. So our contribution here is to apply basically the Moskowitz-Ras PCP theorem in this reduction. And to make it more general purpose, we also form like a standalone reduction from label cover to set cover. And this allows us actually to obtain some tighter hardness results with some plausible stronger assumptions, such as the projection games conjecture, which tells us that if that holds, then the same kind of lower bound holds, even if we allow the running time to grow exponentially in the number of sets, which usually has not been the case for any of these algorithms. Now, I'll briefly touch on the results for the directed Steiner tree problem, and the result for the other problems followed by the same approach. So in directed Steiner tree, you're given a directed graph. It has costs on the edges. You're given a collection, a subset of the nodes are terminals, and then you have a designated root, R. What you want to find is a rooted tree, namely a tree with R as a root and directed from the root called arborescence, and it should contain X, the number of terminals. And the objective now is to minimize the cost of this tree, namely the sum of the cost on the edges in the tree. And notice that this is actually a proper generalization of set cover. Suppose you, for instance, basically construct the following tree. That, sorry, this is an acyclic graph. So here you have the sets in the set cover instance, and here you have the elements. And the elements are the terminals, X. And what you now want to basically find is a collection of which of these sets do you actually want to choose so as to cover all the terminals. And the cost of the set can be now the cost of the edge going towards that set node. And we present a very simple algorithm for this. You kind of guess what are the internal nodes of the tree. Guessing means we can try all possibilities, all such brute force, try all such subsets. And then given such a set, we first compute an optimal arborescence that contains this set, those nodes. But then we use that set as the source of the roots to use to find collection of trees to cover the terminals. Namely, we use C essentially as the sets in a set cover problem. So we essentially turn it into a set cover problem that we can then solve in a similar way. The only catch here is that we need to balance the size of the set because we find it by brute force and the size of the sets. So our algorithm is really only effective when you're trying for a fairly large sub-exponential time, when alpha is greater than half. So I leave you with one open problem. What about the case when alpha is less than half? And I will stop here. Thank you for listening.